Great. Welcome everyone to the Wisconsin Robotics Seminar Series. Before I introduce our speaker, just kind of some quick reminders. The seminar series is held the first Wednesday of every month, 1 p.m. Central Time. This is the last semester, the last one of the semester, and we'll start up again in the fall. Mike, by the way, if I state something incorrectly, please jump in and correct me. The other thing I wanted to mention is make sure that you join the email list if you haven't, which is available on the Wisconsin Robotics website, so you can be aware of the future talks that we're going to be given. Let's see, the format and flow of the seminar. It's a 45-minute talk, and then we'll have 15 minutes available for Q&A. During that time, because of the virtual format, if you have questions, ask in the chat or the Q&A, however it's listed on the whatever virtual meeting format system we're using, and we'll have people ask the questions, and I think there may be some ability to ask in person, and if that's the case, then you can do that. So I'd like to introduce Professor Chitalia. Professor Chitalia is from the University of Louisville, and he's the director of the Healthcare Robotics and Telesurgery Laboratory, so HEART, small EA, capital RT laboratory for short. He's, as I mentioned, he's in the University of Louisville. His pedigree, he's got his PhD from Georgia Tech in mechanical engineering, a master's in electrical engineering from the University of Michigan, and a bachelor's degree in electrical engineering from the University of Mumbai in India. And prior to joining the ME department at Louisville, he was a research fellow at Boston Children's Hospital, Harvard Medical School, working with Pierre DuPont. As the director of the HEART Lab, his research is focused on semi-autonomous, micro and mesoscale surgical robotics with a focus on development of dexterous intelligent robot tools. And so he employs a wide range of methods to improve the operation and control, including microscale machining, 3D printing, and modeling of superelastic structures and joints. So in today's seminar, Professor Chitalia will describe some of this work. The title of his talk is Tiny and Not So Tiny, Continuum Robots That Bend and Twist. And I'm certainly looking forward to your talk. So without further delay, I'll pass the lectern over to Professor Chitalia.
Thank you so much, Dr. Zen, and good afternoon, everyone, to today's presentation. I hope all of you can still hear me fine. And like Dr. Zen said, today's presentation is going to be about some really tiny and some not so tiny continuum robots for surgeries. Before I begin, here's a little bit of a recap of what Dr. Zen already said. Like he said, I'm the director of the Healthcare Robotics and Telesurgery Laboratory here at the University of Louisville, Kentucky, where we build some of these tiny and not so tiny robots for surgeries. Prior to that, just about 6 months ago, I was at the Harvard Medical School and Boston Children's Hospital, where I worked on some of the continuum robots you will see in this presentation today. Some of the even smaller robots that I worked on back at Georgia Tech, I'll also be talking about those in today's presentation. So let me begin by sort of a brief breakdown of today's presentation. First, I'll talk about the really, really tiny robotic microcatheters, which in the medical field we call guidewires. Now, we designed what is one of the smallest robotic guidewires in the world at only about 0.4 millimeters. So it's a really tiny robot. I'll talk a little bit about the design of the robot, some of the mechanical modeling that informs the design, and so a little bit about the controls of the guidewire itself. And then I'll carry on the theme to talk about some of the larger scale robotic catheters that I've been a part of in the past, especially at Harvard. We modeled these catheters because it turns out these sort of unique actuation modalities for continuum robots are already being applied in surgeries out in the field. So if you've heard of the Auris catheter or the Auris bronchoscope from Johnson & Johnson and some devices that are used especially for heart valve repair, they have this very common actuation modality that is both tendon-driven and concentric tube. Now, turns out we were the first ones in the world to actually propose a mechanical model that sort of describes the behavior of this unique sort of actuation strategy of these unique catheters. And so I'll talk a little bit about that as well. So let me then begin by motivating the first area of my research a little bit. Cardiovascular disease, whether it be in the form of coronary heart disease or stroke, high blood pressure, heart valve disease, etc., is the leading global cause of death, accounting for about 17 to 20 million deaths globally on an annual basis. In fact, the number of deaths from cardiovascular disease exceed those from all types of cancers combined. Now, peripheral artery disease, or PAD, is a type of cardiovascular disease in which blockages or occlusions are formed at the extremities of the person's body. So I'm talking arms and legs, right? And about 120 million people live with this condition today. Now, endovascular treatment or minimally invasive treatment of PAD has gained prevalence in recent years, and that has been associated with lower trauma to the patient, shorter hospital stays, lower risk of amputating the deceased limb, and lower risks of mortality. So endovascular or minimally invasive treatment of PAD is indeed, in fact, all cardiovascular diseases is indeed proving to be very effective. Now, manual navigation of a long and thin microcatheter called a guidewire to the target blockage or occlusion is often the first step in the minimally invasive treatment of any cardiovascular disease. So what is a guidewire? A guidewire is basically a long and thin wire, typically made of some sort of a super elastic biocompatible material like nickel, titanium, or nitinol. And these wires go anywhere between 0.3 millimeters at the lower end to 0.8 millimeters at the higher end in terms of their diameter. And they're about a meter long. So they're really long and thin, right? And once these guide wires have been manually navigated to the target blockage, then a variety of catheters can be advanced over this guide wire to the blockage to treat the deceased limb or the deceased artery or vein, right? Now, while guidewire technology has improved over recent years with hydrophilic coatings, highly torqueable guide wires, and so on being available in the market, manual navigation of a guide wire through vascular anatomy, which is very tortuous, is often a very time-consuming and challenging endeavor. Increased operation time also leads to increased radiation dosage, not only to the patient, but also to the clinician and the nursing staff that's present in the OR room, right? Increased vascular tortuosity, especially around the disease, also leads to kinking or breaking of the guide wire. And you can see that happening in the bottom right of the slide here. The guide wire is being advanced through a fairly benign, fairly straightforward artery. But you can see it gets stuck here at this point and starts looping over itself. And it cannot be advanced further, even though the artery is fairly straightforward. And so all of these sort of shortcomings of manual guide wires require us to address them by designing a robotic and steerable version of the guide wire, which is exactly what we did when we designed the coaxially aligned steerable robotic guide wire, which we call the Coast guide wire, which you can see in the video playing on this slide. Now, the Coast guide wire has an outer diameter of only 0.4 millimeters. So to give you guys an idea of what that is, 0.4 millimeters is about 3 or 4 of your hairs. So extremely, extremely small and long. Now, the critical feature of this guide wire was that it features a completely decoupled and independently controllable bending joint angle. And you can see that here where I'm changing the angle of bending of the guide wire, but I can also independently control the length of the bending portion of the guide wire. And you can see me doing that on the slide too. And this, again, is extremely difficult to achieve at these small scales. And I'll explain why that is important in a couple of slides. But first, let's actually dive under the hood of this coast guide wire and see what's underneath. So the wire you see on this page, on this slide, is actually a 4-layered structure. It consists of an outer tube and a middle tube. The outer and middle tubes are notched or micro-machined super elastic nickel titanium or nitinol tubes. And the micro-machining pattern that we employed here is known as a unidirectional asymmetric rectangular notch pattern, as you can see on the figure to the left. Also note that for the outer and middle tubes, the notches were 180 degrees offset from each other. And the reason we do that is because these tubes are designed to slide within each other, right? And so we don't want any mechanical interference when these tubes slide within each other, all right? Now, within the middle tube, we have this stainless steel inner tube. And the purpose of the stainless steel inner tube is simply to add stiffness to the non-bending portion of the guide wire. So therefore, translating the tip of the innermost tube allows us to control the length of the bending portion of the guide wire in turn. So that's how we can control that bending length that I was talking about. Now, within the inner tube runs the single nickel titanium tendon, which is about 15 microns in diameter. So again, very, very small and thin, almost like a spider web. So this tendon runs through the innermost tube and then is terminated on the inner wall of the distal tip of the middle tube. And on actuating this tendon, that is by pulling on the tendon, I can control the angle of the bending segment of the guide wire. So by actuating the tendon, I can achieve a control of the bending angle. And by translating the innermost tube, I can control the length of the bending portion of the guide wire. So both of those can be controlled. So all tubes and tendons are then connected to an actuation module. I'll talk a little bit about the actuation module on the next slide. But therefore, we have 5 control variables at our disposal while controlling this guide wire. We can control the roll motion of the entire guide wire. So we can bend in basically any plane. Then we can control the tendon stroke, which controls the angle. We can control the length of the bending portion using the translation of the innermost tube. Then the control variable X3 here to the bottom right of the slide controls the displacement of the outermost tube. And I'll explain why that is important in a couple of slides. While X4 controls the displacement of the actuation stage itself. So by translating X4, I can insert and retract the guide wire within the person's body, within the patient's body, right? So here, let me talk a little bit about the actuation module. We designed this very, very compact actuation stage for the coast guide wire, despite the number of degrees of freedom that we have. The diameter of this actuation module is only about 4 centimeters, so it's very, very handheld. And the idea is that the clinician will simply be able to dock this actuator stage onto this translation stage, and then they can control the entire guide wire remotely. So a couple of slides ago, we talked about how the coast guide wire features a completely decoupled and independently controllable length, bending joint length, and bending angle, right? And those are very important because it allows us to perform what is known as follow the leader motion using the coast guide wire. And this type of motion is already very difficult to achieve at large scale. So the fact that we were able to achieve this at these small scales by itself is a significant contribution. But what I mean by follow the leader motion is that when I'm advancing the guide wire, for instance, here you can see on this video again, the body of the guide wire kind of follows the tip precisely. And that's what we mean by follow the leader motion. And so how is that different from just having a single joint that is, it's a serial revolute joint, let's say a continuum robot with a revolute joint, and I can simply insert or retract the guide wire. Why is that different? And the reason is because let's say I did have a revolute joint. Let's say my finger here is a revolute joint, and I bent the guide wire and I translated it within the person's body. Well, even if I bend the tip and translate it, I'm still going up or down. The body of the guide wire is really not snaking along behind the head, right? That's what we critically need if we're going to traverse tortuous vascular anatomy. So we do, in fact, need follow the leader motion when we're performing sort of cardiovascular or PAD type of surgical procedures. And as you can see on the slide, follow the leader motion can be implemented at any feasible angle in the robot workspace, including these very, very tight 180-degree turns. Now, for targets that are not reachable using follow the leader motion, what we could do is we can simply advance the outermost tube by translating this tube. If you remember that there was a control variable that was assigned to the translation of just the outermost tube. What this allows us to do is it allows us to feed forward the distal tip of the guide wire while retaining curvature at some anatomical bifurcation, right? And this type of motion is what we call feed-forward motion. And feed-forward motion, much like follow the leader motion, can be implemented at any feasible angle in the robot's workspace. So then, if we're to build a kinematics model, for example, for this type of a robot, we then need to understand the structure of the robot and the behavior of the robot itself, right? So to do that, we must first understand the micromachining pattern and what that does to the individual tubes in the coast guide wire. So to do that, what we did was we analyzed our micromachining pattern, and we find that for the pattern that we use, there's about 4 variables that we can change while doing the micromachining. We can vary the depth of our notches. We can vary the spacing or the width of the notches. We can vary the spacing between 2 consecutive notches given by this variable h. And we can control the number of notches, which controls the length of our entire joint, right? What this micromachining does, specifically this variable d here, that is the depth of the cut, what that does is it makes the second moment of area of this tube and the location of its neutral plane, that makes it a function of the arc length. So as our arc length goes from the base of the robot to the tip of the robot, let's say from 0 to 1, the second moment of area of the tube along that arc length becomes a function of that arc length because of this micromachine. And that's critical. We'll find out why that is critical in a couple of slides. The other key sort of limitation that happens as a result of the micromachining is that femtosecond laser, which is how we micromachine these tubes, those sort of sparkly heat treat the nickel titanium, resulting in a little bit of pre-curvature that sort of compounds over the length of the guide wire, resulting in a small amount of pre-curvature that is machining induced into the guide wire, the individual tubes of the guide wire. And this micromachining induced pre-curvature simply cannot be eliminated. We try to minimize it, but we cannot eliminate it. Now, the other key limitation is that our robot is an extremely slender robot. Now, in continuum robotics literature, a slender robot is defined as one that has a length to outer radius ratio of about 20 or 30. That's considered traditionally a slender robot. Well, in our case, the slenderness ratios are as high as 500. So our beams, the individual tubes of our robot, are extremely, extremely slender beams. And they undergo a large amount of deformation just from their own weight. And this deformation depends upon the direction of gravity. So you can see that on the slide here. There's a slight amount of pre-curvature in this tube. It's the same tube, by the way, that's pointing both up, and then it's twisted to point down. And you can see that the amount of pre-curvature in the beam varies vastly depending upon whether the tube is facing up or down. And when it's facing down, look at the amount of pre-curvature in this tube. So finally, we want to design a coast robot that when completely assembled, it doesn't curve like this, right? We want it to be relatively straight. So we want a low total pre-curvature in the robot. But we also want to retain a certain amount of compliance, because you might ask, well, why do you even bother machining these tubes then, right? If you don't want any pre-curvature, don't machine the tubes. But, well, I do want to be able to control the tubes using the tendon, right? So to add that compliance, we do need to machine them so we can control them using the tendons, but we also don't want them to be highly curved, right? So that's how a little bit of mechanical modeling sort of informs our design. And so the way we model each of the tubes in the Coast robot is we model each tube as a pre-curved cantilever beam that has a non-uniform cross-section and is uniformly loaded by gravity, right? And I won't belabor the point too much, but the Euler-Bernoulli equation for such a beam is given to the top right of this slide here. Here on the left-hand side, kappa of x is the required curvature that we want to know. And the right-hand side is very interesting because kappa naught is that machining-induced pre-curvature that I was talking about. And that only depends upon the machining parameters, like the depth of the cut, right? But then we have these terms, m of x, which is the applied bending moment due to gravity, and I of x, which is our second moment of area. Now remember, both I and the distributed load are dependent upon the cross-sectional area at each point along the arc length. So they're a function of arc length. So in other words, they're a function of the shape, but the shape is a function of the applied load. So how do we kind of solve this cyclic conundrum? And the way we do that is we apply this method known as the integral method to solve these type of problems. What we do is we use a sort of numerical approach that is iterative. We divide the total load into n steps. So let's say gravity is divided into 1,000 steps. For each load step, we use the previous solution to compute the bending, the shear stress and the bending moment along the entire beam. Then using that, we compute the right-hand side of the Euler-Bernoulli equation. We can assign that a variable h of x. And what's really interesting is we can express the term ds dx, which is an infinitesimal amount of the arc length to the infinitesimal amount of projected arc length. And we can express this ratio as a function of h of x. Now, the key insight here is that the integral of ds, that is a small amount of arc length, should obviously be the total length of the robot, right? Which is a known thing. We know the total length L of the robot. So what we then do is we just search the space of projected length until this integral in terms of h of x meets the required length, right? So that constraint, once that is satisfied, we say that our solution has converged and we move on to the next load step and so on. So that's how we arrive at our solutions. So let's see how we do in both simulation and in experiments. We first simulated in ANSYS using finite element analysis a variety of tubes with a variety of cross sections, a variety of machining parameters, and we showed that our analytical model was very, very well suited to describing the shape that was predicted by the finite element analysis as well. That can be seen to the left and to the right. We machined about 5 or 6 tubes that had various diameters, various micro machining parameters. We hung them pointing up and pointing down. And we were able to show that our model was able to predict their shapes quite accurately as well. So then what happens when we combine these pre-curved micro-machined tubes? So again, like I said, we want to combine these tubes that are 180 degrees offset from each other in a way that their pre-curvatures kind of cancel out. And that's what we did. We used this fairly common equation that is often used in concentric tube robots. And we arrived at about 12 samples that have a very, very low final pre-curvature, right? But like I said before, not only do we want a low final total combined pre-curvature in these tubes, but we also want them to be fairly compliant. And that's what these graphs to the right show. We want to arrive at a solution, and this is kind of the optimal solution we get, that has an overall low flexural rigidity. We want it to be as compliant as possible, but we also want the behavior of the robot to be dominated by the middle tube, because that's where the tendon is connected. And so that's what the solution S4 gave us. So by using this aid of mechanical modeling, we were sort of able to arrive at a design sample that achieved the metrics that we had strived for, that is low pre-curvature, fairly high compliance, and predictable behavior. So then once we do that, we can build a kinematics model for our robot, right? And to all of those in the audience that are familiar with robotics, a kinematics model is basically a block that takes in, especially in continuum robotics, that takes in as its input the desired curvature at a desired bending joint length, and outputs the tendon stroke, that is, how much tendon should I pull to achieve this curvature at a specific joint length X, right? And in traditional continuum robotics, this is a fairly geometric computation. In fact, a kinematics of any serial chain is fairly geometric computation, right? But turns out it's not so for us. And the reason being, if you remember again from a few slides back when I was talking about the design of the robot, our tendons are extremely thin. They're about 50 microns in diameter, 50 or 70 microns in their diameter, which means that basically they're like a spider web. In fact, when I used to assemble these robots, if one of those dropped under the microscope, if I lost them, I wouldn't bother trying to look for it, because the tendon was basically lost into space at that point. So I just had to pick a new tendon. That's how thin these tendons are. Now, what happens when you load one of these tiny spider web-like tendons? Well, it elongates due to strain in the tendon. And turns out the elongation in the tendon was the dominant term in our kinematics model. In fact, the noise from elongation was actually dominating our kinematics. So therefore, our kinematics model not only is a function at the bottom of the slide here, you can see X1, which is the tendon stroke, is not only a function of curvature and bending length, but it also becomes a function of the force that I'm applying. And using the mechanical model that I talked about in the previous slide, we can account for this tendon tension, even though we don't know what it is. And we can express tendon stroke purely as a function of kappa, which is the desired curvature, and X2, which is the bending length. And this is the final kinematics model for this robot. And we were able to validate this model in a paper very, very recently published in TMRB. So now that we have an IK model for the robot, the forward kinematics of the robot is fairly straightforward. But once we have an IK solution for the robot, we then build this control system fairly straightforward. But what's key is that it takes in as its input a trajectory in task space. So what we do is we take the CT scan from an actual patient. We extract, using a software called VMTK, we extract the center lines of the blood vessel that we're analyzing. For example, here you can see an aortic arch and an aortic bifurcation. And what we do is we segment this center line into sections of constant curvature and straight segments. So any vascular trajectory we were able to determine could be divided into straight segments followed by constant curvature segments. And as long as that task-based trajectory was followed, we hypothesized that we can traverse any sort of tortuous vascular anatomy. And so then we feed this task-based trajectory through the IK model. We get a joint space command. We also get feedback here through a PID controller, again in joint space, which is then fed to a motor controller. There's a fair amount of depth involved in the motor control for this type of a robot too. But then that gets fed to the Guidewire. And so let's see how this actually does in a demonstration. So Here we have a phantom aortic arch for the same patient whose CT scan we saw on the last slide. And here's an X-ray view of the guide wire performing follow the leader motion. And whoops, sorry. So let me go back here. What's key, what I wanted to sort of show was that this aortic arch is not necessarily in the horizontal plane, even though the X-ray makes it look like it is in the horizontal plane. So by controlling the roll motion of the guide wire, we're able to roll it and perform follow the leader motion in any given bending plane. So let's see how it does. And right now, the guide wire we've designed in the lab is fairly small in its total length. And so it can only do about one turn around any tortuosity. And so here you can see it perform follow the leader motion for an aortic bifurcation. Again, this is a fairly tight curve that's not necessarily horizontal. And you can see the guide wire kind of snaking around, fairly tight turn there. So then that takes me kind of to the second area of my research, which is the theme is fairly common. That is, this type of robot is also for cardiovascular applications, but it's fairly large in its diameter. So the diameter of this robot is about 6 millimeters compared to the 0.4 millimeters of the Coast robot, but it also features a higher number of degrees of freedom. So the control or modeling this type of a robot becomes fairly challenging. So let me talk a little bit about the motivation behind this type of a robot. Again, it's for cardiovascular disease, and is fairly commonly applied today in surgeries in cardiovascular disease. So you might have heard of, again, like I said, the Oris robot from Johnson & Johnson that has a similar structure to this. But on this slide, we have the Edwards Pascal device, which has an inner sheath and an outer sheath. Both these sheaths are now tendon-driven. Unlike in the Coast guide where there was only one, oops. I feel like my sharing seems to have stopped. Is that right?
Yeah, I don't see it.
All right, let me pull that up again. Is that?
Yep,
all
it's
right,
back.
we're back on. All right, I must have lost Zoom for a second there, but I believe you were on this. Yeah, we were on this slide. So traditionally, going back to what I was talking about, we see in the industry these type of robots that are concentric and coaxial, like the Coast robot, but they're each of those tubes are now tendon-driven, right? Now, traditionally in continuum robotics literature, we have been exposed to concentric tube robots or tendon-driven robots, right? Concentric tube robots are basically pre-curved nitinol tubes that are inserted one inside the other, and translation and rotation of each of those tubes causes deflection of the tip, right? So we have 2 degrees of freedom per tube there. And then on the other side, we have the second approach, which is generally tendon-driven robots. These are very akin to standard serial chains, where we have either one or more serial joints. Each of the joints are driven by one or more tendons to be 1 or 2 degrees of freedom. And we can control the tendon stroke, or we can control the tendon tension, right? But because this is a serial chain that has a limited number of joints, it can't do the kind of follow the leader motion that we want it to do, like we saw in the Coast Guidewire, right? And so in recent years, this sort of hybrid approach of concentric tube tendon-driven robots has been applied in both academia and in industry. So here to the bottom right, we have a real-life example of a MitraClip delivery device, which is a way to repair a deceased mitral valve in the heart. Now, in this case, for each of these robots, we have 3 degrees of freedom per tube. We can pull at its tendons to control the bending angle. We can translate each tube with respect to each other. So we can slide one tube over the other and so on. And we can rotate the individual tubes. But turns out, in academia at least, we've modeled robots like this without considering the rotational degree of freedom. What we say is, well, you don't really need rotation. We can either rotate the base like we did for the Coast robot, or we can have multiple tendons to account for rotation. But turns out rotation is actually a very, very key degree of freedom in the actual industry. And you can see that being done here in the mitral clip GIFs that are playing to the bottom right. Here you can see the clinician needs to be able to rotate. In fact, the mitral clip there, once it has been brought through the septum orthogonal to the mitral valve, the clinician needs to be able to rotate it to sort of orient the mitral clip device perfectly with respect to the mitral valve. So this is a fairly important degree of freedom that hasn't been accounted for previously in literature. And that's what we did in our recent paper to ISMR. What we found was that when these sort of concentric tube tendon-driven robots are loaded, that is, tension is applied to their tendons, not only do the individual tubes bend, but they also significantly twist with respect to each other. And that twist had not been modeled in literature. You cannot really see the twist in this slide here, but I have a picture in a later slide where this twist becomes extremely obvious. So therefore, our objective in this work was to generate a complete mathematical model for these concentric tube tendon-driven robots that not only accounted for individual tube bending, but it also accounted for individual tube twisting. So to do that, we sort of took support of this very traditionally applied method to model continuum robots, which we call a Cosserat rod model. And basically, a Cosserat rod model is a way to describe any beam's behavior in space. And to be able to implement a Cosserat rod model, you need basically four things, right? You need to know the position of the center line of the entire beam, indicated by this variable P. You need to know its material orientation that's given by this triad of this coordinate frame here, given by these blue, green, and red axes. In this case, we used a Fennet-Serret frame. It's called a Fennet-Serret frame, also a tangent normal binormal frame. But you could also use a Bishop frame to do the same thing. And then, in addition to knowing the position and orientation of the beam, one also needs to know the curvatures, that is the angular strain rates and the torsion in the beam. And we also need to know the linear strain rates, that is the shear and elongation in the beam at all times. And those are given by these variables U and V. So if we know P and R and U and V, we can basically, and we know their evolution along the length, we can determine the entire shape of the robot. And so these are the Cosserat rod equations. So these determine the evolution of P and R, and that's fairly straightforward. It's given as a function of U and V. But U and V in turn depend upon the internal forces and bending moments internal to the beam. And they are given by this constitutive model here. The K terms in this matrix are simply the stiffnesses of that beam. So KBT is the bending stiffness, and KSE is the linear stiffness. So basically, it depends upon the elastic modulus of the beam, shear modulus of the beam, and all that good stuff, right? So once we have a constitutive model, we also have these equilibrium equations that tell us the evolution of the internal forces within the beam. So that's kind of all we need, right, to describe the entire shape. We know the evolution of P and R, and through N dot and M dot, we know how U and V evolved as well. Turns out, although we don't really have the entire picture, we don't yet know what the external forces are on this beam, or do we? We actually do know the scalar values of the applied forces, right? We know what tension is being applied through the beam. So we know the scalar magnitude of the force we're applying at the tip. We assume no friction for this paper. So we know the scalar force applied. We don't yet know the vector of that force and the applied force, right? So this kind of becomes a very classic 2-point boundary value problem. And the way we solve, because what we do know is we know the location of the base of the robot. So we know P and R at the base of the robot, and we know the force that is being applied to the tip of the robot. So we have these boundary conditions at the base and the tip. So what we do is we implement a shooting method. We say, all right, we know the P and R position and orientation at the base. We don't know U and V. So let's just guess, all right? Let's make a guess, an educated guess. And then let's propagate our equilibrium equations till we get to the tip. From that, we can compute P, P dot, and P double dot. And using that, we can determine the force vector and the torque vector that is being applied to the tip. Then we compare that to the internal forces and bending moments within the beam at the tip. And when those kind of balance out, we say that, well, we've reached a solution. And we kind of do that exact same thing even when we have two Cosserat rods, right? When you have two independent Cosserat rods, ideally you would have 6 times n unknowns now for n tubes, because you would have 3 u variables and 3 v variables for each tube, and then you have n tubes, so you have like 6 n unknowns. But the key insight here was that these are concentric tubes, so they have a common center line, right? So a lot of these variables go away. So basically, you know what the cross-sectional shear strains in the two beams are, and they're exactly the same. We also know that the curvatures of the two concentric beams are going to be exactly the same. In the XY direction, the beams are allowed to twist with respect to each other. The beams are allowed to elongate with respect to each other. But the X and Y direction, angular and linear strains are one and the same. So the number of unknowns in our case reduces to 8. We also have 8 equilibrium equations, 4 for X and Y and 4 for Z. So in summary, what we kind of get, we get this sort of very beautiful 8 equations, 8 unknown situation that screams out invertible matrix, right? So it's a very convenient sort of situation for us. And then we simply apply what we did for the single Cosserat rod. We have, instead of a 2-point boundary value problem, in this case, we have a multi-point boundary value problem. We know the position and orientation at the base of the robot. We know the force being applied to the individual tubes at their distalmost point, and we know the force being applied at the very end of the robot, right? So we know these sort of boundary conditions, and so we apply, again, a shooting method, and we check at these midpoint and endpoint boundary values. When we check against that, once we've sort of achieved convergence between the applied forces and the internal forces and bending moments within the individual beams, we say that we've converged and we found a solution. So really quick, let me talk a little bit about how this did in actual experiments, right? So here, let me draw your attention to the top right of the slide. Here you can see this sort of 45-degree angle picture that I took of the two tubes, and you can see that when the two tubes are loaded, they indeed do twist quite a bit. You can see the tubes are almost behaving in a corkscrew-like manner, which has not been modeled in literature. So what you can see in this red curve to the top left is previous models proposed in literature that had just single tubes, multiple tendons. They did not really capture this twist, whereas our model is able to almost perfectly predict the extent and the presence of this twist. And then we also we also conducted about 32 experiments for various configurations of this robot, where we either stuck out the inner tube within the outer tube. We, by different lengths, we changed the angle between the tendons of the two tubes. That is, we rotated the tubes with respect to each other. And then we also applied different tendon loads. And our average error in predicting the distal point of the robot in each case was only about 3 to 4% of the total length of the robot, which is very, very a standard amount of error, especially considering all the Cosserat rod literature. This is very, very much what the error has been observed for Cosserat rod models in continuum robotics in the past. So in conclusion, this model can correctly predict not only bending, but also twisting behavior when you have these sort of coaxially aligned tendon-driven robots. And the key sort of interesting thing about this robot modeling strategy is that not only does it apply to concentric tube tendon-driven robots, but because this is a very general model, it also applies to concentric tube robots and tendon-driven robots separately. So this really is that one model to rule them all, so as to say. So with that, I think I'm at the end of my talk. I can take some questions. Thank you.